Okay, good morning. So today we will be starting with a new chapter. I was supposed to start with the numericals of the filter designing, but after that it will be a long holiday. So I decided to cover the applications of biomedical signal processing today. So coming to the applications of the biomedical signal processing, as we have already discussed that the biomedical signals we generally consider are the signals which are being generated by the body, say for example ECG, EMG, EOG, ERG, right? So we want to see how the processing of these signals they can be used for various applications. Okay, so course outcomes. So we already know the course outcomes of this course, so I'm not going into the details again. So coming to the applications, so uh, what is the aim of the biomedical signal processing? Right, we have previously discussed about the main aim of the digital signal processing and all these things. So the main of the biomedical signal processing is to extract relevant information from the biological signals. Okay, so the information it may have either clinical, biochemical, pharmaceutical relevance, and it may help us in understanding various biological phenomena, disease diagnosis, and predicting human health. Okay, now among the various biopotential signals that are being studied, the most widely studied biopotential signals they include ECG, EEG, electroencephalogram, EOG, electrooculogram, electromyogram or myograph, and phonocardiogram. Okay. Now, processing of these signals can be used for health monitoring, designing rehabilitative devices, and evaluating treatment outcomes. Okay. So, when we talk about applications of biomedical signal processing, it can be categorized into several parts, okay, or you can say several domains. The first one is rehabilitation engineering, where we try to integrate the differently able persons with the society. Okay, then in medicine, suppose you want to treat a patient, how he is doing to the how he is responding to the treatment, that may be analyzed, and biomedical signal processing it can help us in evaluating the treatment regime which is being offered to the patient. Okay, then third is disease diagnosis. Suppose someone is having a problem associated with the ocular muscles, okay, or the movement of the eye. If we analyze the electrooculogram, it can help us in understanding whether there is any movement related disorders with the eye, or whether there are, since EOG is basically the dipole which is being created uh, while created between the due to the potential difference between the retina and the cornea. Okay, so if in the corneal layer if there are any problems, then EOG may also give some information from there. Okay, then next is understanding human psychology and behavior. It can also be done. Suppose when we are depressed, how do we know that we are depressed? We basically go for the analysis of the in electroencephalogram grams which we acquire, or we go through certain questionnaires, and from there we can understand the psychological behavior of a patient. Okay. Then we have smart devices. In the smart devices, it is usually associated with the rehabilitation devices. However, um, rehabilitation engineering it encompasses a lot of smart devices. Okay, similarly when we talk about the medicine, over there also we can use various smart devices which can help us in analyzing the treatment modality and disease diagnosis also. So we have kept it separate, this topic, this smart devices, because development of this device can also be an application. Okay, apart from using these devices into different domains. Okay, so uh, in today's lecture, I will be discussing about some of the examples uh, of this application of biomedical signals, which can be used for various biomedical application purposes. Okay, so the first one is application of the speech signal. When we talk, a signal is being generated, and that signal is nothing but the speech. So we give, we can generate different types of speech. Okay, and this, when we use this speech signal to control some rehabilitative devices, then such a system is called voice controlled system. Okay, you all must be knowing about the Alexa, right? So what is an Alexa? You give a command to Alexa, and Alexa will help you performing those tasks. Say, Alexa, put on this music. Alexa, do this. It will say, put on the fan or put off the fan. Whatever you, whatever the command, voice command you will be giving, Alexa, which is basically a an AI controlled device, which will analyze your voice, and from there it will generate some control signals to control the different devices. Okay, so how it can be helpful in rehabilitative devices? Okay, one classical example is the example of a patient who is quadriplegic. Quadriplegic means both hands and both legs, they are not working. Okay, usually what happens, this kind of patients, they are being transferred from one place to the other using wheelchair, right? So you can use this voice controlled uh, systems, voice control system, to control this wheelchair. Okay, so what would be the probable commands? The probable commands would be, say, right, left, forward, and also backward. Okay, so how do you do that? Basically, one of the simple example is that we have to acquire the voice signal first. So we acquire the voice signal, then we do some processing on the voice signal, say up to this. So what we get, say we do squaring of the voice signal, then we perform the smoothing, then we give some multiplier so that we can enhance the quality of the signal, then we can get some collector means it will acquire a set of data, and then it will analyze the data. Then after the collection of the data is done, we can go for the peak detection, and from there we can go for the detection of the amplitude ranges. Okay, so based upon the amplitude ranges, we can categorize the sound level into three levels, say high, medium, low. So here in this study, only three levels have been designed. However, we can use other information also, and we can increase these sub levels. Okay, so here we are having three commands: high, medium, low, but we can generate more sound levels also by manipulating the signal. Okay, so what is happening over here, right? Look into this region, what is basically happening? So once you get the voice signal, if you have seen voice signals, they are somewhat bipolar signals like this, right? Then squaring of this, what it will do, it will put all the signals on the top side. Okay, unipolar signal, it will be converted. Then when you do the smoothing, what it does, smoothing is basically an envelope detector. Okay, multiplier, what it will do, it will you'll be getting an envelope, something like that. This multiplier, what it will do, it can help you in increasing the amplitude levels of the what you call the envelopes. Okay, then collector means, suppose you have done this, so you have collected this portion of the signal, and then you have gone for the peak detection. After peak detection, you can find out the amplitude of this signal. Okay, now up to this part, if you see, if you compare these ranges, depending upon the amplitude ranges, we can generate three command: high, medium, low. But how do you know that when you are normally talking, the system will not take those as the command, and it will initiate the this rehabilitative device? In that case, what will happen? क्या होगा? The device will be activated unintentionally, but we don't want that. In those cases, we can include a switching device which will generate a high or a low input, output, and that will be analyzed. The output will be analyzed by the comparator, and when we are getting the commands as the output of this amplitude range and from the comparator, when both are high, then only the ultimate control signals will be generated. Okay, so this will ensure that what is happening is that it will ensure that the device is not activated under unintentional due to unintentional voice commands. Okay, so this is a simplest form of an voice command system where we are not basically actually uh, detecting the what words have been told, but what we are doing, we are just looking into the amplitude levels. So if you see over here, the envelope is something, it looks like here, acquired voice signal. Okay, so processed voice signal, if you see, it is an envelope, it is right like this, and then acquired switching signal would be there. When both are high, then you can generate a control signal of high. Okay, similarly we can generate three levels of the control signals for controlling the device in different modes. So herein I have given the example of a wheelchair, but it can be used for other devices also. Say for example, you want to analyze the signal for, say, putting on the fan or putting off the fan. It can be used over there also, and the applications are endless. The main thing is that how do you generate the control signal? So that is more important. Now if you want, you can make such a system wireless by using various wireless protocols. One of the wireless protocol is the Zigbee wireless protocol. Okay, so if you see the voice signal acquisition module, it is there. Then it has been integrated with Arduino, uh, which has been further integrated with the Zigbee module, and from those module it can send the information, the control signal information, to a remote device. Okay, which is attached with another Zigbee module, and it is acting as a receiver. Okay, and it is acting as a receiver. So if you generate, because when you send a signal wirelessly, there has to be some receiver, sender and receiver, or you can say transmitter or receiver. Okay, so because of that you need both a transmitter and the receiver units while you are transferring any signal wirelessly. Okay, so what is the advantage of this wireless voice controlled system? The main advantage is that you can make the device very compact and it can be placed onto the human body itself. Suppose you make a pocket size device and it is being put into the pocket of the person. So it would be quite handy, right? and then it will be easier for him to give the command. Otherwise, if it is a wired system, it will always be connected with the, say, wheelchair for our example. Okay. Now, if the person is, suppose, he is not quadriplegic, he is paraplegic, and both of his leg it is not working. Okay, but he is able to use his hands and all this thing. So he wants to get himself transferred from the bed to the wheelchair, and the wheelchair is, say, 100 meters away from his bed. So he can give the command easily that to bring the wheelchair near to him, and then get himself transferred to the wheelchair. So the, if you see, the extent of independence of the patient, it is increasing. When we talk about rehabilitation, what is rehabilitation? Rehabilitation is the integration of the patients to the society so that they can do most of their work independently, right? So by incorporating the wireless modules, we are basically increasing the independence of the patient. Okay. So there is a video demonstration. So I'm not going into that. You please go through it, uh, because we are very tight in time schedule, right? Now, similarly, what we can do in the previous case, what we have done, we were not actually detecting the speech. What are the voice commands? We were just looking into the amplitude levels. Okay, but it might not be very convenient for the patient. There are, in many cases, you will find that there are degenerative diseases. So in those cases, what will happen is that the person may slowly lose the capability to generate the same quality of the voice signal. Okay. So you might have seen in many cases what happens, the voice become very low. So what will happen in that case? So you have to recalibrate your system at regular intervals. Okay, but that is not user friendly. So what to do in those cases? It would be easier for us if we can use speech recognizers. If we can use speech recognizers. Okay.
So past in that previous application, like when we are analyzing the amplitude levels like high, low, and medium. So how the signal, like how it is understanding, like to move right, left by that high, low, and
That's a very good question. Anyone else who can answer?
like maybe like high is set for right, medium is set for left. Is that the thing?
Yes, exactly. If you go back, you see when the amplitude levels are greater than 1800, it is considered as high. So you give the command that if the amplitude levels are 1800 or more, then you consider it high, and one of the digital outputs of your microcontroller will be put on a high mode. So it would be associated with some control. When you are talking about wheelchair, there will be either servo motor or the DC gear motor. So DC gear motor, they will give you more power. So usually in wheelchairs you have DC gear motors. Okay. So there are two DC gear motors because there will be two wheels, right? So you give the command. Suppose you want to move forward. If the amplitude levels is high, in the high mode, then both the DC gear motor, they will move forward. Then at that time, what will happen? The wheelchair will move forward. Suppose you give left DC gear motor, it remains uh, low. Output of for that DC gear motor is low. That means it will be put off. whereas the right one, it will start moving. Okay, so what will happen? This is closed, this is moving. So what will happen? The wheelchair will move towards the left. On the other hand, if the right DC gate motor is put off and the left is being moved, the wheelchair will be moving towards the right. Right? So in that way, you give the microcontroller command that if your amplitude range is say above 1800 or 1800 1850, okay, or 1900, something like that, and above, then you perform this task. If it is say medium, you move the wheelchair to the left. If it is say in the low category, move the wheelchair to the right. So you have to train the person. Okay, so training is important over here. Okay, however, as I told you, there may be some degenerative diseases due to which the voice amplitude level, it may get disturbed. Okay, so you have to recalibrate the system every time. So what is the way out? The way out is if we can use a speech recognizer. We can use a speech recognizer. So in the speech recognizer, what we have basically is that one of the very common speech recognizer is your Google. In the Google app, you will be having speech recognizer. If you speak something to the Google app, what it will do? It will recognize the word and it will display the text. So we can use that. One of my students, they use that to develop a home automation system for them. So what we did is that, again over here the problem of false activation may be there. So we don't want that. So what we did is that we attached a Hall effect sensor with an Arduino, and when a magnet which is attached to the patient, it was brought in contact with the Hall effect sensor, what it will do, it will be sensed by the Arduino, it will generate a command, and that command will be sent through the Bluetooth module which is attached to the Arduino to the mobile. So over there, what it will do, it will initiate an app, and this app would already be there. So it will initiate the app to launch Google Speech Recognizer. Okay. So once that is there, so this activation signal, it will activate the speech recognizer, and then you talk over there to the Google Speech Recognizer. So it will generate the text. Now this text command, it will be sent to the Arduino through the Bluetooth module again, and it will be processed within the Arduino itself, and control signals will be generated. So if there is a high signal, say for example USB powered lamp will be blown, and if it is high signal in the other port, the fan may be initiated. Operation of the fan may be initiated. Okay. So in this way, what is the advantage? You can increase the number of the commands as per your wish. In the previous case, when we were talking about the amplitude levels, it becomes difficult to go for the what you call, to generate larger number of commands. Okay, because you have to train the person very carefully, and if by mistake he is not able to generate the command of particular amplitude, then there will be malfunctioning of his wheelchair. Okay. However, when we are talking about the speech recognizer, whether you use the Google speech recognizer or not, that's a separate case. But if you use the speech recognizer, then what you do is that the options are unlimited. Suppose over here the student has worked on USB powered fan, put the fan on, put the fan off. Okay. Now, he, suppose you want to regulate the speed, you can say after putting on, increase the level to say 1 or 2 or 3. So that can also be done by using the speech recognizer. Over here, the student just showed. So this was the app. App was one, and the through the Bluetooth module, the control signal was sent by the HC0 this Google Speech Recognizer. It was put on. Then from there, what happens is that it opened this connection and it said, "Okay, you give the commands." So say it is all on. Okay. So during that position, during that condition, both fans and in this thing light, it would be put on, and then when they give the command all off, both the things would be put off. So these are just the conditions which has been shown. You can individually also put on or put off the devices. A demonstration of the device, it has been all shown over here in the YouTube, so you can go and you can look into that at a later stage. Similarly, what we can do is that we can also generate control signals by the movements of the eye. Okay. So what happens is that when we are uh, trying to move, see, when the eyes are being moved right, the nature of the signal is different. When the eyes are moved left, the nature of the signal is different. When the movement of this eyes towards the upper side, the movement is different. Okay. And then down, the signal operations are different, and when the person is blinking, it is having a different kind of signals. Okay. So if you see over here, there are two electrodes inside. One electrode is to capture up and down, and the other set of electrodes are on the either sides of the eye. Okay, on the either side of the head. So even though you are able to watch the signal in the same plot, but these signals are being generated by the two channels. So one channel is the this one, channel 1, and the other one is the channel 2. And depending upon from which channel we are getting the signal, we can generate, see, we can glow the LEDs, different LEDs over there. Okay. So here you see, among all these signals, if you see the signal of blinking, its amplitude is very high. Okay. So in this way, we can generate a large number of signals. Okay. Control signals, and those can be used for modulating the direction of the wheelchairs or any other appliances. We can also go for the uh, different combinations of these signals. Suppose you are moving your eyes twice frequently, so that the nature of the signal would be different in that case. Okay, so you can extract the features from that, and you can uh, tell that this would be my this specific command. So here also you can see we can go for the modulation of the generation of the control signals of different characteristics just by moving the eyes. Okay. So what happens over here? So if you see, there are two channels, channel 1 as I told you, and channel 2. There are two signal acquisition system. the signals were being acquired by the Advantech DAQ system, data acquisition system. Then from there the control signals were generated. Then they were being sent through the RF transmitter to the wheelchair model which we designed. It was basically a robotic vehicle. Okay, so if you see how the microcontroller output, uh, we we got the microcontroller output, and the combination of that, it helps us in moving the wheelchair in different direction, either forward, backward, right, left, start. Okay, and this plus means clockwise and minus sign means anti-clockwise direction. Okay. Application of the EMG signals. These are this is similar to what we have already discussed for the voice control. What we do, we go for the what do you call squaring of the signal. Then we find out the envelope, and then we can go for whatever processing we want. Okay, so just by moving different fingers, suppose we are placing the EMG sensor just above our wrist, and just by moving the different fingers, we can generate EMGs of different characteristics. So over there also, if you find that the options are unlimited to generate the control signals for what you call for controlling the rehabilitative devices. Okay. Again, we can make it wireless, so it will improve the uh, flexibility for using the devices. Okay, so here we can get an what do you call this demonstration of a device what one of the student he has developed. Now this is important application of the biosignals to design multimodal assistive system. In many of the cases, if you see, uh, it would be easier if we work with a certain sets of commands. Okay. Now, when we talk about say of a what do you call this patients who need help, so he may be needing help in different aspects. Say, for example, he wants to pick up a call. His his system may be attached with a mobile phone. Okay, and he wants to pick up a call. Okay. Also, he wants to modulate the movement of the wheelchair. So how to do it? If you look into the output ports of most of the microcontrollers, they are quite limited. So how to do that? Okay. So what we did is that one of my student, we attached different Hall effect sensors. Just it was a demonstration. We attached two Hall effect sensors. Now these two Hall effect sensors were being could be activated with a single magnet. Okay, so when this Hall effect sensor, when this magnet is brought in contact with the Hall effect sensor one, then one of the system would be activated, and if we take it to the other one, then the other system will be activated. Okay, herein here, so there are some examples. So herein what we did is that we have shown the activation of a robotic arm, and the second one was for the robotic vehicle. So you would say why these two? This is because uh, when we started this, we saw that there was a problem uh, for the wheelchair patients. Suppose wheelchair is giving them the opportunity to move in and around. Okay, say in the home or the office. However, suppose if there is a what do you call, an object which has been kept on a shelf. So while sitting, how will he reach the object? Say for example, the projector is here. So I want to reach to the projector. Just by sitting on the wheelchair, I am not able to reach. So this is also a disability. Okay. So this is a problem for a differently abled person, right? So in that case, what to do? So many researchers have told that if we attach a robotic arm on the wheelchair itself, then this projector would be within my reach. Okay, but how to control that? Then again, sitting there, I can use some joystick or something like that. I can reach to it. But suppose the same thing can be done if we if the person is still on the bed. Suppose he just needs a glass of water. So he need not to just transfer himself from the bed to the wheelchair and then go there, get the glass of water, and again get himself transferred to the bed. So it will be problematic for him. So if you make a wireless system, so what we can do, just sitting on the bed or lying on the bed, you can control the composite device of the say wheelchair and the robotic arm, and he can access the glass of water. He can bring it near to him, and then he can use it. Okay, so we have to look into improving the convenience of the patient, how we can make them more and more convenient. Okay, so such a system where using a same control system, you are basically able to um, what do you call control two different systems, then which has been integrated, then that integrated system, it is regarded as multimodal assistive system because it is capable of doing multiple things. Okay, then application in arrhythmia and detection. Arrhythmia, you must have already studied in your biomedical instrumentation class. Professor Shivaraman, he might have been teaching you about the ECG signals and how it can be used to analyze different types of um, analyze the ECG signal to understand what are the different diseases. Okay, so first one is, it is the ECG for a second degree in a partial block. Okay, then this one is atrial fibrillation. Then third one is ventricular tachycardia. Fourth one is your ventricular fibrillation, and then third one is third degree block. Okay, so when we talk about arrhythmia, arrhythmia is basically what you call the irregular electrical activity of the heart, and due to that irregular activity, the heart does not perform as we expect it to perform, give its performance. Okay, so we can get these ECG signals, then we can pre-process the signals. We can go for the heartbeat segmentation, then we can go for the feature extraction, and from there we can develop certain artificial intelligence techniques for classifying the different kinds of arrhythmia. Okay, you getting my point? Apart from that, yeah, ECG, it can be used for analyzing the ANS activity. ANS is um, autonomic nervous system. Yeah, ANS is autonomic nervous system. So it is basically having two subsystems, parasympathetic and sympathetic nervous system. Now, both these systems, they have innervations onto the SA node. So by analyzing ECG, we can go for RR interval signals, okay, and by analyzing the RR interval signals, we can go for the analysis of the autonomic nervous system in a non-invasive manner. And this is one of the easiest way to study the ANS system in the non-invasive manner. So what we do over here, suppose this is the ECG signal what you get, then from there through the peak detectors, the RR intervals, they are being calculated, and then an RR interval signal, it is being generated, which looks something like these boxes, these points are there. Then there is an averaging of this signal. Now this signal, this average red signal, it is called RR interval signal, or in some books you will find it as HRV signals, heart rate variability signals. Okay, so you can, so see, we have completely transformed one signal to another signal so that we can get information about the ANS, which is totally a different system. This over here we are basically understanding the activity of the heart muscles of the heart. Okay, while we are transforming by certain signal processing techniques, what we are doing, we are analyzing the autonomic nervous system. We have gone into the analysis of the nervous system. So you can see the power of our signal processing techniques. We can transform a given signal, and from there we can try to get some information of another system. Okay, so I'm not going into all the details. So when we talk about the heart rate variability, as I told you, we have parasympathetic and sympathetic nervous system, which gives us a measure of the ANS behavior. Okay, so in literature you will find that there are frequency domain parameters, which gives a more clear picture about the ANS physiology. Usually, the main HRV parameters, they include VLF, very low power, very low frequency, high frequency, low frequency normalized unit, low frequency, high frequency normalized unit, VLF percent, LF percent, HF percent, and LF by HF ratio. Okay. So what are these? Basically, once you get the RR interval signals, you find out the power spectral density basically by performing the Fourier transform. So you will get some this thing like this, and then you can look into the frequency spectrum over here. If you see, the frequency spectrum has been mentioned over there. Whatever is your power information in that, so that is called the VLF of that this thing. And for the percentage, what we do for the percentage calculation, we calculate the values of VLF, the total area of the VLF, LF, HF, okay, and then from there you find out the what is the mm, percentage of say VLF or LF or HF. Okay, then LF by HF ratio, it is another measure which has been quite convenient, uh, most frequently used. So what does this indicate? It indicates that the decrease in the LF by HF ratio, it means that there is an increased parasympathetic activity. Okay, a decrease in LF by HF ratio means there is an increased parasympathetic activity. Okay, then SSVP signal, I am not going into the details. These are basically the EEG signals. After we go for this flashing of the eyes through the through a LED through a LED panel. Okay, so this LED panel is put in front of the eye of the volunteers, and then the lights are being flashed onto the EA, and then EEG data are being recorded. So it is called steady state visual evoke potential. So you must have studied in biomedical instrumentation about VEP, right? So SSVEP is nothing but a special kind of VEP, visually evoke potential, where we are giving some flashes of the light, and due to the flashing of the light, how it is affecting our brain signals, we are measuring that. Okay, so this is a brain cap, EEG cap, which has been put to acquire the signals. Then what are the different bands of the frequencies? There are 7 bands: delta to theta, alpha, low beta, beta, high beta, and low gamma. Okay, and these are the frequency ranges of these signal components. Okay, so when you do this EEG analysis, you can get the activity, which part of the brain is being activated the most. So at different frequencies of the flickering of the light, it will generate different brain mapping. So it is called brain mapping. Okay. Then this is how you can do the pre-processing. So this is the original signal. Then you can band limit the signal, and after band limiting, you can apply some filtering techniques like moving averaging, averager or something to get a good quality signal to proceed further. So these are the different channels. Nassian means nose, and Indian means our backside. So accordingly, we are having different electrode positions. I'm not going into this. Oh, yeah. So thank you. If you have any questions, we can discuss. So this was just just my mm, what do you call? It was my try to give an understanding how signal processing it can be helpful for you in the how is brain mapping done. Uh, uh, it's a very complex thing. However, the thing is that what they do is that you have the electrodes. Then from the electrodes, you can have these amplitude values. So when you get these amplitude values, so wherever the amplitude value is higher, you say that at that location the activation is more. Okay. But underlying, there are lot more things going on. What program you will be selecting for the amplitude EA, amplitude detection, and all these things. So a whole lot of programs are there. But basically, this is the so in this way we find out the brain mapping, which part of the brain it is being more activated compared to the other part of the brain.